Park, Treasure Valley communities,
the El Paso, Las Cruces communities,
Eastern Iowa communities,
Mid-Michigan communities.
We are extremely proud of the quality, balanced journalism that CBS 4 News produces.
But we are concerned about the trouble and trend of irresponsible, one-sided news stories
plaguing our country.
The sharing of biased and false news has become all too common on social media. More alarming, some media outlets publish these same fake stories without checking facts first.
The sharing of biased and false
news has become all too common on social media.
More alarming, some media outlets publish these stories simply aren't true without checking facts first.
Unfortunately, some members of the media use their platforms to push their own personal bias and agenda to control exactly what people think. And this is extremely dangerous to our democracy.
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 Imagine if a highly infectious pandemic, like the Spanish flu outbreak in 1918 that killed more than 50 million people worldwide, happened today. In our modern world that is so connected by land, sea, and air, how long do you think it would potentially take for the pandemic to spread globally? Would you have enough time to react? The answer may surprise you. Now imagine an empty professional hockey rink representing Canada. You arrive early for the game and are the only one in the arena. Unexpectedly, a water pipe running across the rink's ceiling begins to leak a drop. The drop represents a person who has been infected with the flu. 1 minute later, 2 drops fall, representing 2 more people infected with the flu. And then 1 minute later, it doubles again to 4 drops, and so on. With the drops doubling in numbers every minute, how much time do you think you will have before the rink fills with water and reaches your seat? Minutes? Hours? Days? Weeks? Months? The answer is approximately 30 minutes. The crazy thing is that after 27 minutes or so, only the ice is covered with water. So sitting high up on your perch, you think you're safe, that you have plenty of time to take action. But due to exponential growth, you really only have about 3 minutes left before the water completely rises to the top of the rink and infects you with the flu. If a flu pandemic outbreak did go entirely exponential, the speed it would spread across Canada and the world could be deadly. Let that sink in.
And yet, human intuition has a hard time really recognizing what it means sometimes. We can anchor on a sequence of small-seeming numbers and then become surprised when suddenly those numbers look big, even if the overall trend follows an exponential perfectly consistently. This right here is the data for the recorded cases of COVID-19, aka the coronavirus, at least at the time that I'm writing this. Never one to waste an opportunity for a math lesson, I thought this might be a good time for all of us to go back to the basics on what exponential growth really is, where it comes from, what it implies, and maybe most pressingly, how to know when it's coming to an end. Exponential growth means that as you go from one day to the next, it involves multiplying by some constant. In our data, the number of cases in each day tends to be a multiple of about 1.15 to 1.25 of the number of cases the previous day. Now, viruses are a textbook example of this kind of growth, because what causes new cases are the existing cases. So if the number of cases on a given day is n, and we say that each individual with the virus is exposed to, on average, e people on a given day, and each one of those exposures has a probability p of becoming a new infection, then the number of new cases on a given day is E times P times N. And the fact that N itself is a factor in its own change is what really makes things go fast, because if N gets big, it means the rate of growth itself is getting big. One way to think about this is that as you add the new cases to get the next day's count, you can factor out the N. So it's just the same as multiplying by some constant that's bigger than 1. This is sometimes easier to see if we put the y-axis of our graph on a logarithmic scale, which means that each step of a fixed distance corresponds to multiplying by a certain factor. In this case, each step is another power of 10. On this scale, exponential growth should look like a straight line. Looking at our data, it seems like it took 20 days to go from 100 to 1,000, and 13 days to go from that to 10,000. And if you do a simple linear regression to find the best fit line, you can look at the slope of that line to draw a conclusion like we tend to multiply by 10 every 16 days on average. This regression also lets us be a little more quantitative about exactly how close the exponential fit really is. And to use the technical statistical jargon here, the answer is that it's really freaking close. But it can be hard to digest exactly what that means if true. When you see one country with, say, 6,000 cases and another with 60, it's easy to think that the second is doing 100 times better, and hence fine. But if you're actually in a situation where numbers multiply by 10 every 16 days, another way to view the same fact is that the second country is about a month behind the first. Now this is of course rather worrying if you draw out the line. I'm recording this on March 6th, and if the present trend continues, it would mean hitting 1 million cases in 30 days, hitting 10 million in 47 days, 100 million in 64 days, and 1 billion in 81 days. Needless to say, though, you can't just draw out a line like this forever. It clearly has to start slowing down at some point. But the crucial question is when? Is it like the SARS outbreak of 2002, which capped out around 8,000 cases? Or the Spanish flu of 1918, which ultimately infected about 27% of the world's population? In general, with no context, just drawing a line through your data is not a great way to make predictions. But remember, there's an actual reason to expect an exponential here. If the number of new cases each day is proportional to the number of existing cases, it necessarily means each day you multiply by some constant. So moving forward d days is the same as multiplying by that constant d times. The only way that stops is if either the number e or p goes down. It's inevitable that this will eventually happen. Even in the most perfectly pernicious model for a virus, which would be where every day each person with the infection is exposed to a random subset of the world's population, at some point most of the people they're exposed to would already be sick, and so they couldn't become new cases. In our equation, that would mean that the probability of an exposure becoming a new infection would have to include some kind of factor to account for the probability that someone you're exposed to is already infected. For a random shuffling model like this, that could mean including a factor like 1 minus the proportion of people in the world who are already infected. Including that factor, and then solving for how n grows, you get what's known in the business as a logistic curve, which is essentially indistinguishable from an exponential at the beginning, but ultimately it levels out once you're approaching the total population size, which is what you would expect. True exponentials essentially never exist in the real world. Every one of them is really the start of a logistic curve. Now this point right here, where that logistic goes from curving upward to instead curving downward, is known as the inflection point. There, the number of new cases each day, represented by the slope of this curve, stops increasing and instead stays roughly constant before it starts decreasing. So one number that people often follow with epidemics is the growth factor, which is defined as the ratio between the number of new cases one day and the number of new cases the previous day. So just to be clear, if you were looking at all of the totals from one day to the next, then tracking the changes between those totals, the growth factor is a ratio between two successive changes. While you're on the exponential part, this factor stays consistently above 1, whereas as soon as your growth factor looks closer to 1, it's a sign that you've hit the inflection. This can make for another counterintuitive fact while following the data. Think about what it would feel like for the number of new cases one day to be about 15% more than the number of new cases the previous day. and contrast that with what it would feel like for it to be about the same. Just looking at the totals they result in, they don't really feel that different. But if the growth factor is 1, it could mean you're at the inflection point of a logistic, which would mean the total number of cases is going to max out at about 2 times wherever you are now. But a growth factor bigger than 1, subtle though that might seem, means you're on the exponential part, which could imply there are orders of magnitude of growth still waiting ahead of you. Now, while it's true that in the worst case situation the saturation point is around the total population, it's of course not at all true that people with the virus are randomly shuffled around the world's population like this. People are clustered in local communities. However, if you run simulations where there's even a little bit of travel between clusters like this, the growth is actually not that much different. What you end up with is a kind of fractal pattern, where communities themselves function like individuals. Each one has some exposure to others, with some probability of spreading the infection, so the same underlying and exponential inducing laws apply. Fortunately, saturating the whole population is not the only thing that can cause the 2 factors we care about to go down. The amount of exposure can also go down when people stop gathering and traveling, and the infection rate can go down when people just wash their hands more. The other thing that's counterintuitive about exponential growth, this time in a more optimistic sense, is just how sensitive it is to this constant. For example, if it's 15%, like it is as I'm recording this, and we're at 21,000 cases now, that would mean that 61 days from now, you hit over 100 million. But if through a bit less exposure and infection, that rate drops down to 5%, it doesn't mean the projection also drops down by a factor of 3, it actually drops down to around 400,000. So if people are sufficiently worried, then there's a lot less to worry about. But if no one is worried, that's when you should worry.
That must not be named is likely to impact the U.S. healthcare system suggests that all available hospital beds will be filled by around May 8, 2020, if the outbreak tracks with Italy's figures and 10% require ICU. On March 6, 2020, Liz Sprecht, a PhD in biology and associate director of Science and Technology for the Good Food Institute, laid out her concerns. I think most people aren't aware of the risk of systemic healthcare failure due to the outbreak because they simply haven't run the numbers. So let's do the math. Let's conservatively assume that there are 2,000 current cases in the U.S. today, March 6th. This is about 8 times the number of confirmed cases. We know that there is substantial underdiagnosis due to the lack of test kits. I'll address implications later of under and overestimate. We can expect that we'll continue to see a doubling of cases every 6 days. This is a typical doubling time across several epidemiological studies. Here I mean actual cases. Confirmed cases may appear to rise faster in the short term due to new test kit rollouts. We're looking at about 1 million U.S. cases by the end of April, 2 million by about May 5th, 4 million by about May 11th, and so on. Exponentials are hard to grasp, but this is how they work. As the healthcare system begins to saturate under this caseload, it will become increasingly hard to detect, track, and contain new transmission chains. In absence of extreme interventions, this likely won't slow significantly until hitting much greater than 1% of the susceptible population. What does a caseload of this size mean for the healthcare system? We'll examine just 2 factors: hospital beds and masks, among many, many others that will be impacted. The United States has about 2.8 hospital beds per 1,000 people. With a population of 330 million, this means about 1 million beds. At any given time, 65% of those beds are occupied. That leaves about 330,000 beds available nationwide, maybe a bit fewer at this time of year with regular flu season. Let's trust Italy's figures and assume that about 10% of cases are serious enough to require hospitalization. Keep in mind that for many patients, hospitalization lasts for weeks. In other words, turnover will be very slow as beds fill with patients. By this estimate, by about May 8th, all open hospital beds in the United States will be filled. This says nothing, of course, about whether these beds are suitable for isolating patients with a highly infectious illness. If we're wrong by a factor of 2 regarding the fraction of severe cases, that only changes the timeline of bed saturation by 6 days in either direction. If 20% of cases require hospitalization, we run out of beds by about May 2nd. If only 5% of cases require it, we can make it until about May 14th. 2.5% gets us to May 20th. This, of course, assumes that there is no uptick in demand for beds from other non-outbreak causes, which seems like a dubious assumption. As the healthcare system becomes increasingly burdened, people with chronic conditions that are normally well managed may find themselves slipping into severe states of medical distress, requiring intensive care and hospitalization. But let's ignore that for now. All right, so that's beds. Now, masks. The feds say we have a national stockpile of 12 million N95 masks and 30 million surgical masks, which aren't really ideal, but they're better than nothing. There are about 18 million healthcare workers in the U.S. So, let's assume only 6 million healthcare workers work on any given day. This is likely an underestimate, as most people work most days of the week. But again, I'm playing conservative at every turn. As cases saturate virtually every state and county, which seems likely to happen any day now, it will soon be irresponsible for all healthcare workers to not wear a mask. These healthcare workers would burn through the N95 stockpile in 2 days if each healthcare worker got only 1 mask per day. 1 per day would neither be sanitary nor pragmatic, though this is indeed what we saw happen at the epicenter of the outbreak, with healthcare workers collapsing on their shift from dehydration because they were trying to avoid changing their personal protection equipment suits as they cannot be reused. So how quickly could we ramp up production of new masks? Not very fast at all. The vast majority are manufactured overseas, almost all in China. Even when manufactured here in the U.S., the raw materials are predominantly from overseas. Again, predominantly from China. Keep in mind that all countries globally will be going through the exact same crises and shortages simultaneously. We can't force trade in our favor. Now, consider how these 2 factors, bed and mask shortages, compound each other's severity. Full hospitals plus few masks plus healthcare workers running around between beds without proper PPE equals a very bad mix. Healthcare workers are already getting infected even with access to full PPE. In the face of personal protection equipment limitations this severe, it's only a matter of time. Healthcare workers will start dropping from the workforce for weeks at a time, leading to a shortage of healthcare workers that then further compounds both of the previous issues. We could go on and on about thousands of factors like the number of ventilators or even simple things like saline drip bags, but you see where this is going. Importantly, I can't stress this enough. Even if I'm wrong, even if I'm very wrong about core assumptions like percentage of severe cases or current case numbers, It only changes the timeline by days or weeks. This is how exponential growth in an immunologically naive population works. Undeserved panic does no one any good, but neither does ill-informed complacency. It's wrong to assuage the public by saying only 2% will succumb. People aren't adequately grasping the national and global systemic burden wrought by this swift moving of a disease. I'm an engineer. This is what my mind does all day. I run back-of-the-envelope calculations to try to estimate order of magnitude impacts. I've been on high alarm about this disease since about January 19th, after reading clinical indications in the first papers emerging from the epicenter. Nothing in the last 6 weeks has dampened my alarm in the slightest. To the contrary, we're seeing abject refusal of many countries to adequately respond or prepare. Of course, some of these estimates will be wrong, even substantially wrong, but I have no reason to think that they'll be orders of magnitude wrong. Even if your personal risk is very, very low, don't mock decisions like canceling events or closing workplaces as undue panic. These measures are the bare minimum that we should be doing to try to shift the peak, to slow the rise in cases, so that the healthcare systems are less overwhelmed. Each day that we can delay an extra case is a big win for the healthcare system. And yes, you really should prepare to buckle down for a bit. All services and supply chains will be impacted. Why risk the stress of being ill-prepared? Worst case, I'm massively wrong, and you have a big bag of rice and a big bag of black beans to burn through over the next few months. One more thought. You've probably seen that multiple respected epidemiologists have estimated that 20 to 70% of the world will be infected within the next year. If you use the 6-day doubling rate that I mentioned, we land at about 2 to 6 billion infected by sometime in July of this year. Obviously, I think the doubling time will start to slow once a sizable fraction of the population has been infected, simply because of herd immunity and a smaller, susceptible population. But take the scenarios that I just mentioned: full beds, no personal protection equipment at just 1% of the U.S. population infected, and stretch them out over just a couple of extra months. That timeline roughly fits with consensus endgame numbers from these highly esteemed epidemiologists. Again, we're talking about discrepancies of mere days or weeks in one direction or another, not disagreements in the overall magnitude of the challenge. This is not some hypothetical worst-case scenario. This is reality, as far as anyone can tell, with the current available data. For Headlines with a Voice, this is Nancy Morgan-Hart.